Assalamu alaikum, how you doing, guys? Today we're going to talk about the shear and diagonal tension in beams, and that's going to be the second part, namely after we were done with the design of the beams for flexure. Now we're going to tackle the design for shear. If you look at this diagram, actually, to be quite honest with you, I usually spend about 25 to 30 minutes on this slide, if not more, and that's kind of an interaction between me and the students in class. So we really discuss the various things that going on here, and I rely more on their input. But since this can't be done at the present time, so what we have in front of you is a 4-point bending test. There is no web or shear reinforcement in here, and we can see the different zones. There's almost like 3 zones. Let's call this zone 1, zone 2, and this is similar to zone 1. So in this area here, we only have a pure flexural cracks, okay, as you can see. And you will notice that usually the flexural cracks go up into the upward direction, and they're not wide. On the other hand, if you look at the web failure or the shear failure around here, they start out smaller, and then they take some sort of a bend, and we're going to talk about that in the next slide. One of the things that we actually emphasize is why do we need shear reinforcement? Well, in Flexure, we always told you that my primary concern in the design is to ensure that we have yielding in steel so that we can have a ductile failure. So if I have a ductile failure, then I have time to actually do some maintenance, maybe warn the occupants. And that was one of the emphasis that we had during our designs. Now, shear, on the other hand, usually a shear failure is quite sudden. So there are no warnings. It will just happen, as it did with this beam right here. So this one failed immediately at the reaction at this high shear point. So to avoid that, we like to use what we call shear reinforcement or stirrups down the road, and these will help in preventing this let's say sudden collapse, and will also ensure that I would have a flexural failure before I will have shear failure. As I said, the whole issue is, or our main goal is, try and avoid the shear failure, as it is sudden. It's similar to brittle failure, so it's complete total collapse, and this is one of the big no-nos in design. So let's see what happens here. So if I look at this beam again right here, different beam, I'm loading it with distributed load. Let's call this W, and here I'm looking at the neutral axis, and I'm going to take an element 1 right here. As you know, at the neutral axis, we usually have 0 bending stress, but maximum shear stress, okay, as we have learned that from strength of material. So again, my bending stress, sigma, is still equal to MC over I. My shear stress is equal to VQ over IB, which means now element 1 is under pure shear, which means now that my principal stresses will be at 45 degrees, and that will transform into 2 tension forces. This is tension force, and here I have compressive force. So now, as you see, since I said tension, we know concrete is weak in tension. So as soon as these tension forces develop, then we are going, if they are more than the rupture stress of concrete, then failure is going to happen, or let's say the section is going to start to crack. And that's why we call that diagonal tension. So that's mainly because of the principal stresses being at the angle of 45. So if I look at that same beam down here, and then this is my neutral axis, I'm going through that. You've noticed here that this angle is almost 45 degrees. So at the center, or at the neutral axis, I only have shear stress, but I have no bending stress. Now, if I go further from the neutral axis, let's say at a point here, I'm going to have maximum bending stress, but I'm not going to have any shear stress, and that way we can see that the tension is almost flat in this direction. Now, as I start going up or going further away from the neutral axis, let's say maybe at the point here, then I'm going to have both the flexural stress and the shear stress, and then that will also give me some principal stresses, but these principal stresses now are going to be at some angle alpha, and we used to get those angles from Mohr circle, if you remember in mechanics of materials or strength of materials. So you can see now that this angle here is kind of representative of alpha, and then we call these the tension trajectories, which mean the tension is this way and the tension is this way, which means at this point I will open the crack up. Compression on the other hand usually does close the cracks for me. So that's what's happening, and that's why we call these diagonal tension. So it is happening because of the let's say the combination of the shear and bending stress, and that will give me major principal stress at some angle alpha. So that explains then the diagonal tension part. So we have some combination now, and we're gonna obviously discuss those. So there might be a case where I might have a large shear force and large bending moment, like in this simple beam. Again, here's my large moment and here's my large shear. And this is under a concentrated load, let's say P. Now, if I have a distributed load, we know that the maximum moment again is at the center, but we know that we also have zero shear. So at that point here, I'm going to have a large moment, but a small shear force. On the other hand, if I go to the reactions, I will have a very small moment value, but a very large shear. Now, if I'm talking about continuous beams, then in this case, I will have again small values for shear, larger values for M, and the combination like above. So, to remind you, this shows you the shear stress, and this shows you where tau max is. Again, Q being the first moment of area, and then I is BH cube over 12. So then my maximum shear stress is going to be 1.5 times the average shear stress. And I bring that up because we always could relate the maximum shear stress to the average shear stress, which is just simply the shear force divided by the area. And then this factor 1.5 actually differs based on the cross sections that I'm using. If I'm using a circular cross section, then the factor is going to be something different. So you will notice that most of the shear beam tests that were done to come up with the shear equations that we are going to use for design are most of them based on the average shear stress. And lastly, these are also based on linear elastic materials with small deflection, and we know that for at failure, this is not the case for reinforced concrete beams. But again, this is kind of assumption and it's more or less of a starting point. So what happens if I have no web reinforcement? If I have no web reinforcement, so I'm not using any steel or any shear reinforcement, then at a location of large V and small m, there will be little flexural cracking, which is expected prior to development of a diagonal tension crack. Thus, the average stress prior to is going to be equal to V over BD. Okay, and again through tremendous experiments, it was found that this actually is not more than 0.29 square root F prime C, where F prime C is in megapascals or Newton per millimeter square. Okay, again, you will find that most of the shear equations, and I'm going to re-say that again, are based on empirical formula, are based on a lot of shear tests. We start off with, let's say, certain assumptions, with certain understandings, and then build on these as we are trying to build our empirical models. And that was one of the main reasons as that we had some major changes in the shear reinforcement calculations in the 19 code when compared to the 2014 code. Now, if we have regions with smaller shear and large moment, then diagonal tension cracks will be formed at less than 0.16 square root of F prime C. So what happens at a location where I have large V and large M? So what will happen first, these flexural cracks are going to develop first, okay? Now, when the diagonal tension stress, which is what I've showed you in the slides before, at the upper end of one or more of these cracks, which is this crack over here, okay, so there's still some flexure cracking going on over here, then it will exceed the tensile strength of concrete. So the crack now will bend in a diagonal direction, which is the alpha that I talked about. So you will notice now that this is going to be like this, okay? And that's due to the combination of both the shear and the flexure. In the middle here, where there is no shear influence, we only have flexural cracks. And then, as I said, we will have what we call the flexural shear crack. So what happens when I put web reinforcement? Well, the first thing that we should know is for web reinforcement that has no noticeable effect prior to the formation of diagonal cracks. And that means that in the experiment, it was noticed that if we measure the stress in those shear reinforcements, there's actually zero stress. So if there is no crack, there is no stress. It begins to build up as cracks forms. So they really have no influence until we start seeing those cracks, which is after the diagonal cracks have developed. Web reinforcement enhances the shear resistance of a beam in 4 separate ways. So again, it does not have any influence before the shear crack develops, which means it does not preventing it from developing it. Okay, so as long as there's no shear cracks, there's no stress in those shear reinforcement. But the minute that crack begins to start, then we will start seeing some stresses in the shear reinforcement. So they do not prevent the formation of shear cracks. Okay, they're just there to help when they do. Okay, and then the way they do that is that part of the shear force is resisted by the parts that by the bars that traverse a particular track. So usually when a crack is moving along and then it sees the shear reinforcement, then that shear reinforcement will resist that crack. The presence of the same bars restricts the growth of diagonal cracks and reduces their penetration into the compression zone. Like they will prevent the cracks from developing further and moving to the compression zone. So they will resist the crack. They will prevent it from moving to the compression zone. Thirdly, they will also counteract the widening of the cracks, which means they will not grow bigger. Which is also important because as the crack go bigger, you're going to have some separation in concrete. And those three will lead to the fourth one. It will provide some measure of restraint against the splitting of concrete along the longitudinal reinforcement. And since they're there, you will also add to the dowel action that's happening at the longitudinal. So let's say if this is your main reinforcement right here, you're going to have some dowel action. Now if you add a stirrup right here, this stirrup will add to this as well. So the presence of shear reinforcement really helps in preventing or helps in reducing, let's say, the spread and widening of shear cracks or flexural shear. So let's see what happens. So usually we will divide the shear reinforcement or the shear resistance into the following parts. The part one is what we call the uncracked concrete force, which is usually in the compression force. And we usually call that VCZ, or it's a compression due to shear. Then I'm going to have the forces that are coming from my stirrup. Before I continue, I just want to point out this is the crack surface that I'm talking about. Okay, so this crack is traversing these stirrups right here, and here I'm using vertical stirrups with a spacing S. Okay, and then this distance here is what I call the horizontal projection of this crack, right? So just to, again, what are the forces that will interfere with this crack? Again, it's the compression or the uncracked concrete force, which is usually in the compression zone. Then I'm going to have the forces from the stirrups, which is the area of the stirrup times the stress in the stirrup, which we usually call AV times FV. Then I have an interlocking force, and this is usually due to the aggregates of concrete. And then I'm going to have the dowel action that is present in the longitudinal reinforcement. Okay, so these now are parts of the internal shear forces that will actually resist the external force. So now the external force, then the shear force, I can divide that into two parts. The first part, which is coming from concrete only, and these are again coming from the uncracked concrete. It's coming from the dowel action, and this one is coming from the interlocking. And then I have the presence of the shear reinforcement. So if I look at this graph right here, here's my flexural cracking, and then right there, and this tells you the stages at which each one of them will happen. So this is coming from the, again, from the uncracked. This is my dowel action, and this is my interlock action, and this is due to the stirrup. And then we will know that again here I'm going to start having the yielding of stirrups, and once that happens, failure will probably ensue. Okay, so how do I calculate the shear force that's coming from steel? It's just simply the number of stirrups times the area of one stirrup times the shear or the stress in those stirrups. Usually, to be on the conservative side, I will take my projection distance P equal to D. So from that, I know that the number of stirrups is equal to distance divided by the spacing S. And at failure, again, my external shear is supposed to be equal to my nominal shear, and then my nominal shear is going to be equal to the shear which is coming from concrete, and then the shear that is coming from steel. You will notice that these three parameters are actually very hard to determine exactly, but again, from numerous experiments, we will be able always to find, or we have what I call an empirical formula to find, to determine the strength that is due to concrete. As far as the one that's coming from steel, this is just simply the area of the reinforcement times usually the yield stress of the reinforcement. Again, if I'm using grade 60, it's 420. If I'm using grade 40, it's going to be 280. And then D is again the distance from the top compression fiber to the centroid of the longitudinal main steel or the flexural steel, and then S is the spacing between the stirrups. Now, if I have an inclined stirrups like this, again, I'm going to have all these, as far as the shear concrete is concerned, I'm going to have the interlock, I'm going to have the dowel action, and I'm going to have the uncracked compressive force. Now, what might be different a little bit is the force in steel, but if you look at this graph right here, again, the spacing is now this distance. Alpha is the degree that the stirrups are making with the horizontal. I now is the length of the crack, which is this one right here, with P being the projection of that length. Then, and knowing that this angle is making an angle of theta, then I is going to be equal to P over cosine theta, from which I can find A, which is the distance between those inclined stirrups, to be equal to S, which is my spacing right there, divided by sine theta, cotangent theta plus cotangent alpha. From that, I can find what N is, which is simply I over A. Again, now since I is this way and A is this, then N is simply I over A. And I can replace I with P over cosine theta, and then I'm going to replace A with S over sine theta cotangent theta plus cotangent alpha. From that, I will find that my Vs now is equal to N times AV times FV sine alpha. Again, I'm going to replace P with D, and now this is going to be the final equation for the Vs. Okay, so again, so the strength, or what we're going to call the nominal strength of concrete, of reinforced concrete, is simply the shear in concrete, which I'm going to call Vc, plus the shear in steel, or due to reinforcement. We will talk about this in the upcoming recordings, and we will tackle this now. But before we do, we have certain rules to adhere to. And this is where do I take my maximum V? Do I take it at the support? Do I take it at the face of the column? So usually we take it at the face of the column, or it's what we call critical sections, and it is permitted to use at the face of the support. So if this is part of my support, let's say, then, and this is my column, then this could be where I can calculate my shear. Although the other section which most of us use is that between face of support and the critical section located at D from the face of the support, which means I can go a distance D, and then this is going to be my V ultimate max, where I'm going to calculate my ultimate load for non-pre-stressed, and if it's for pre-stressed, that's going to be at a distance H over 2. F, and here's F, A through C are satisfied. A, support reaction in direction of applied shear introduces compression into the end region of the beam, and that's usually if I have a regular beam like that, and I'm putting a load over here, and then this is my reaction. This reaction will introduce compression here, so I can take my ultimate or my critical section at point D. So let's assume I have a continuous beam like that, and then this column actually settles down. Then what will happen here, my reaction now will point downward instead of upward like these. So now in this case, now here I will be introducing tension in the beam, and at that particular time I'm not allowed to take the ultimate at D. In this case I will take it at the face of the column. The second one is loads are applied at or near the top surface of the beam, and I'm going to show that in the next slide, what I mean by that. C, no concentrated load occurs between the face of the support and the critical section. So for that same beam here, if this is the distance D and my load is actually in here somewhere, then my critical section would be at the face of the support, not at D from the face of the support. And these shows the various types that we talked about. Here's what I meant about having the load next to the bottom of the B. In this case, my critical section will be at the face of the support. Now, here I always like to show you at which sections these shear provisions are, so in case something down the road happens, things changed, you will know where to go. And this is the empirical formula in which I'm telling you that the internal or the nominal shear strength is equal to the shear provided by the concrete and the shear provided by the steel. Okay. Now, under no circumstances should my V ultimate be more than this. So basically what I'm telling you here is I'm putting a cap on Vs, which means my Vs should never exceed 0.66 square root F prime CB web VD. So this is the maximum Vs can handle. So if we somehow violate that, then we have either we do that either by increasing F prime C, or increasing B web, or increasing D. Okay, because usually 5 VC is set, kind of. You cannot play with that much. But again, if you increase the same parameters, because they are also a function of these two as well, as I will show you in a little while. Okay, I'm not going to talk about. Okay, for non-pre-stressed members, VC shall be calculated in accordance with 25. And I'm going to show you how we are going to calculate VC. This shows you where VS is calculated, which is in this section, which I will show you in some other recordings. Again, my point of this is actually to show you where you might find these, which sections to look for, in case something happens down the road. If they changed something, that you will not have a lot of trouble looking for these. Now, there's also the issue of how do I deal with D and B web if I have a circular section. So in this case, if I have a circular section, then D now would be equal to 0.8 times the diameter. So if this is 0.8, and this is my circular cross section, and this is my diameter D, then 0.8 D. Okay, I think this is right. So this is as far as this is concerned. B web is the same as the diameter of a solid circular section. So if I have a solid circular section, then this is actually my B web, which is the same as the diameter of that. If I have a hollow circular section, and this is, let's call this thickness T, then in this case my B web is going to be equal to T. Okay, so again, this is how I handle the B web and D and the equations for VC and VS as we down the road. Other thing is my square root of F prime C should never exceed 8.3 megapascals unless allowed in this section right here. But this is, again, this is only allowed if the minimum web reinforcement in accordance with this is satisfied. And this is something, again, I will mention when we talk about the shear reinforcement part, which is going to be in the next recording. Actually, we're going to talk about these in detail. So these are some of the constraints that we have. So what we discussed so far is we had an idea of how the shear strength or shear resistance in reinforced concrete bond is calculated, or we said that's coming from shear from steel and it's coming from concrete. Also, we set where we are going to calculate our ultimate shear. In Flexural, it was easy. We always go for the maximum moment. For shear, it is not. We usually pick a critical section near at the support somewhere, and that's in part also that usually at the supports, at the columns, it's usually heavily reinforced as well. So there's a lot of reinforcement there. So it will be kind of counterintuitive to design according to the support reaction at that location. Instead, we'd like to move a little away from that column, which is usually heavily reinforced at that section. So now these are the equations for VC, and as you can see, these are now the changes that happened in the 2019 code. The one thing that still stayed the same is what we used to call the simple equation, and the simple equation was simply VC is equal to phi 0.17 lambda square root F prime C B web times D. So this is what we call the simple equation. As you can see, it stayed the same. The only thing that we did here, we added now the axial force, which we usually call Nu, and that could be either tension or compression. If it's tension, it's a negative value. If it's compression, it's a positive value. So here, my criteria is, it tells me that if AV is larger than AV minimum, which means I can use this VC if I have shear reinforcement. And we will talk about what I would call the stages of reinforcement. There are certain conditions, and I will leave that to the second recording because it's much more appropriate there, and that will tell me when I'm going to use my shear reinforcement. So at this point in time here, if my AV is more than AV minimum, which means shear reinforcement is present, okay, then at this case I can use VC either of two equations. And when I say either or either of, it does not necessarily mean I have to choose the maximum or the minimum. Although I'm thinking that since there's going to be some time lag between adapting the new code and getting over the old code, I'm thinking that somewhere down the line this will be replaced by the minimum of, because usually this is the minimum of these two. Now here you can see there's the influence of the steel ratio raw, and this is the cubic root times square root f prime c. This stayed the same, so the only difference is the introduction of this equation right here. They eliminated, because I remember in the old code there were a lot of shear equations depending on certain situations and conditions. There were like 7 or 8 of them. All of those got now pushed out, and we only have now these 3, okay, which I usually call them the A, B, and C equation. So usually we used to call these the equation for VC when reinforcement is required. In the area where reinforcement is not required, meaning that AV is less than AV minimum, which means it could be 0, I'm not going to use any reinforcement, then the strength of VC is going to be this equation. So it stops being the simple equation, so we don't use that again, and instead we are using this equation, which we call equation C. So equations A and B are only valid for when reinforcement is required. Equation C is only valid when shear reinforcement is not required, which means your V ultimate should always be less than 5 VC when you are in this stage. If it is not, then you have to go up here. Like I said, this is going to be very well explained in the next slide, because we talk a lot about VS, in the next recording. So in this here now, you've noticed, again, I'm still keeping the 0.66. Lambda, again, is an indication whether I have lightweight concrete, normal weight concrete. In this course here, we're mainly interested in normal weight concrete, so this lambda is usually equal to 1. This is the reinforcement ratio, and this is again simply area of steel divided by B times D, or B web times D. Nu again is the axial force, compression or tension, tension negative, compression it's going to be positive, and this is the area gross, or the gross area of the cross section. So if this is my cross section B and this is H, then area gross is going to be B times H. So this is my gross area. Okay, so to re-emphasize, if I have, or if steel reinforcement is required, then the value of 5VC is going to be either this one, which was usually called the simple equation in past codes, or this one. So again, either means you can choose any one of them. It doesn't matter whether this is maximum or minimum. Okay, me usually I prefer to use the minimum of the two. Again, it's a preference, and I'm sure that somewhere down the line the code is going to change that. The differences are not that much. In certain cases, you're talking about in the order of maybe 20 to 30 kilonewtons, which sometimes could be the difference between using stirrups every 10 centimeters, every 8 centimeters, or every 10 centimeters, or every 20. So just to let you know on that, and we'll talk about this more in the following or ensuing examples. Now, as far as the axial load is concerned, again, it's positive for compression and negative for tension. VC shall not be taken less than 0. So if I have a huge tension force and it will give me VC negative, then VC is equal to 0. There is a cap on the value of VC, and that cap is this. So no matter what you do, VC should not be more than 0.42 lambda square root F prime C B web times D. So that's my maximum VC. The value of NU shall not be taken greater than 0.05 prime C. So if I evaluate NU over 6 area gross, and this is more than 0.05, then I'm going to stick with 0.05 F prime C. And then this is the size modification factor, which is present in equation C. And again, this shows the influence of lambda S. And again, I will be showing you that in the ensuing and following examples in the recordings that are to follow. And you guys have a nice day and stay safe.